How many people have exams tomorrow? Their final tomorrow, like this one. Wow, a lot of you. I'm sorry. I'm sorry. My class doesn't have theirs until next week. So, and out of the kindness of my heart, I made this review session on reading day to not, to keep it equitable all year for those of you who do have it tomorrow. All right, so there is a question here. Oh, okay, got it. What is this? Is the exam multiple choice like the practice exam? The exam is the exact same setup as previous midterm. So there's nothing has changed. So yes, multiple choice, sometimes numerical input. What are the other kinds? Drop down, true and false, so yes, multiple choice. Okay. I'm recording. This will go onto my YouTube channel. You can find that. It'll be public. Okay, so let's get started. So what chapter do we want to start with? 6. Can we do like new stuff first, like 10 through 12? Can we just do a little bit of new stuff and then we'll go back? Oh, also a question about the format of the exam. It's 53 questions. And I like to tell students it assesses each chapter equally. All right, so I think the question is, because like, is it mostly going to be new material? No, not necessarily. Everything's going to be equal because this is a cumulative exam. Okay, so let's do chapter 10 stuff. So let's just go through it. So it's cool. 10, 11, 12, they all kind of have to do with one another. Gases, liquids, solids. We see, whether we see a gas, liquid, or solid at room temperature or pressure has to do a lot about the intermolecular forces and kinetic energy that's on your sample in those conditions. So first we talk about gases. Gases typically have really weak IMFs present. That's why they take on the gas phase at room temperature and pressures. So a lot of really low molecular weight compounds are gases. So okay, so some of these like easier, I would say low hanging fruit questions. All right, this first one: a high altitude balloon is filled with helium at this temperature and this pressure. What is the volume of the balloon at 20 kilometers up high, where the temperature is that, and that's the pressure? So in my mind, this is a gas sample that's changing conditions. Because let's think about the two different kinds of equations we used in gases. We use P1 V1 over T1 equals P2 V2 over T2, the combined gas law. We use that equation. We also talked about PV equals nRT. So like, when do we use which equation? That's like the question of the year. Because they're both similar. They both have P's, T's, that's when do we use what? So my hint here is if your sample is changing conditions, we have a sample, you put it in one condition and then you change it. All right, like you change the temperature, you change the pressure, you change the volume, whatever. You use the combined gas law because we have P1s, we have P2s, we have T2s. So you have a sample and you change its conditions. Because if we have a sample, we have a set number of moles of gas and all we're doing is changing the conditions, but the amount of gas is staying the same. So versus PV equals nRT, typically we use that equation when we're just describing one condition and we just want to calculate like the moles of gas that are present, or the pressure of a certain amount of gas, how much pressure that exerts or something, but we're only talking about one condition. So that's the difference between these two equations. If you squint really carefully here, they actually are the same equation. PV, the combined gas law and the ideal gas law are the same equation. So for question 1, which equation do we use? The combined or ideal? Which one? Combined, yes, because we have a balloon on the ground and then we're putting that balloon 20 kilometers up in the air. So we're going to be using this information that's given. Here is V1, there's T1, there's P1. Actually, is that T1? When I put T1 into this equation, do I put 21 Celsius? No, it has to be in Kelvin. So that's the caveats here. When you use P1, the combined gas law, temperature needs to be in Kelvin. So this would be 294 Kelvin. All right. T2 also needs to be in Kelvin, so you need to convert that. But volume, it can, for the combined gas law, can be in any unit as long as they match. V1 and V2 just need to match. Same thing with pressures. P1 and P2 just need to match. So if we look here, there's T2 and there's P2, our new different pressure. We have to change one of the pressures so they match. So for me, I would change torr to ATM. So 63 torr divided by 760 torr would change that to, ATM, whatever that is. That would be P2. And then at that point, it's plug and chug. So a little distractor here would be that 20 kilometers. That's not part of our combined gas law or the ideal gas law. But we use all the other pieces of information. I'm reading a book right now. It's called, and not reading it actually, it's an audio book. So I'm being lazy. My eyes are being lazy. So I'm just using my ears. It's called Caesar's Last Breath. It's about gases and like chemistry. I'm trying to do better about history and like the consequences of chemistry throughout history. And I learned that gas in Greek, all right, has a root. That word gas has roots in Greek, and it means chaos. Does that make sense? Like connected to kinetic molecular theory, like, yeah, gases are really chaotic versus, liquids or solids. Yeah. Also, argon is Greek. Argon, right, on our periodic table, is Greek for lazy. I like that. Yeah, because it's a noble gas, right? Yeah, so I like that. All right. Okay, I'm not going to do the math. You see so it's just plug and chug. You just need to make sure your V's match, your P's match, and your T's are in Kelvin. That's it. Okay. So let's look at the second one. Gases are sold in large cylinders. What pressure in atmospheres will be exerted by 2.5 kilograms of oxygen when stored at this temperature at this volume? Which equation do we use? Combined or ideal? Ideal, because this is just one condition, right? So our ideal gas equation, PV equals nRT. Pressure, volume, N is moles of gas, R is our gas law constant, and T is in temperature. This equation, it does matter what units you put in. To make it easier, it's best to just know the one of the forms of R, our gas law constant. You're actually going to be given this. This R, one of them for the ideal gas law is 0.08206, but the detail here is the unit. This unit is liter ATM over mole Kelvin. So the unit of R tells you what the unit of pressure has to be in volume, N has to be in moles, T has to be in Kelvin. So in this equation, it does matter what unit you put in, all right? It is important. So it's just easiest to convert your pressure to ATM, convert your volume to liters. So here our temperature is 22 Celsius. So temperature would be 295 Kelvin. There's our volume, it's already in liters, and we want the pressure in atmospheres. But if we look here, the last piece of information, weren't directly given N number of moles of gas, but that's okay because we were given kilograms of gas, in this case, oxygen. So how would we go from, how can we, get all of the knowns in this equation? We have P, or no, we don't, but that's what we want. We want V, or we already have V. R is a constant. We're given T. How can we get N with the information given? Moles. Yeah. So N is moles. So to go from kilograms or grams to moles, we just use the molar mass of oxygen. What's the molar mass of oxygen gas? Okay. Yeah. Wow. You all yelling at each other. Be nice. Be nice. Yes. So, yeah, that's a trick question because I just heard oxygen gas. So we got to be clever and know what is the form of oxygen gas on Earth. Is it O atom? No. So the molar mass is not 16. It is actually 32 because O2, when we think of O2, it's O2 gas. O2 gas. So it's 32 grams per mole. So, So let's do that. So 1.5 kilograms of O2, want to convert that to grams. So 1 kilogram is 1,000 grams, 32 grams is 1 mole of O2, and then that equals some number, all right, whatever that is, and then that's what you plug into that N, and then you solve for P, and that's it. All right, and then that pressure will be in atmospheres because of the unit of R. What's the other R that we talked about? There's another R that you will be given on the exam, so this is one of them. The R that we use for the gas law constant. The other one is 8.314 joule mole Kelvin. We use this R, it's actually the same R, I promise. It's just the unit is different. We use this when we're concerned about energy terms. So we use this R when we talk about root mean square speed of gas particles. So it's also involved in gases. So the equation for root mean squared velocity is 3 RT over molar mass of your gas. So there's another R. So do know there's two different R's, both involved gases. You use 8.314 for root mean squared. You use the small one for Pivnert. Okay, all right. Okay, so 3 is about partial pressures. All right, so in the previous examples, we had like a pure sample of gas, you know, and its conditions, but in number 3, we actually have a mixture of gases. The air we breathe is actually a mixture of gases, but what's cool is that you can use PV equals nRT on either the total number of moles of gas or any individual component. And this is related to the mole fraction of each of those components. So mole fraction is just the, you know, number of moles of that component over the total moles of gas. So if we look at the pieces of information here, I give you masses of different gases. My strategy here would, okay, let's turn those gram amounts to moles of each. So I know how much moles of N2 I have. I know how many moles of H2 I have. I know how many moles of argon I have. How do I do those calculations? What piece of information do I need? Molar mass. Okay, very good. So now I have moles of each of the components. This question is asking for the total pressure inside the vessel. So the total pressure will be equal to PV equals nRT, but we want to calculate N total. N total comes from the sum of what we just did. So we would have to take the sum of all of those. And that's how we get P total. So we need to figure out, okay, what's the total number of moles of gas, but that requires us to do molar mass of each of the individual components, all right? We could also PV equals nRT just moles of N2. If we did that, PV equals nRT just this mole amount, we would get the partial pressure of nitrogen. We would get the partial pressure of hydrogen or partial pressure of oxygen. And so that will allow us to answer this next question real easily. Which gas possesses the largest mole fraction of the mixture? If you just look at the mole amounts and whatever is present in the largest quantity, that's going to have the largest percentage, all right, the largest mole fraction. Because you just take each of those components and divide by the total moles. And so, you know, all those mole fractions that you get for each component should add up to 1 in that case. You can see it on the key. I show it there. I just want us to walk us through the thought process there. Okay. Okay. All right. So I think if you do that, the total number of moles is like 2.3 moles of gas, and you can just PV equals nRT it and you get pressure. All right. So what's really cool about the ideal gas law is that the identity of the gas, it doesn't matter. If I had 1 mole of hydrogen gas or 1 mole of neon, it's going to exert the same pressure if all the other conditions are the exact same. As long as the number of particles are the same, the identity does not matter in terms of PV equals nRT. All right. But what does change when we have different gas samples is density of them. And that's what goes on to number 4. Number 4, because what's the difference between a helium balloon and a balloon that I blow up with my lung air? Is there a difference between those kinds of balloons? One's going to float, one's not going to float, right? Why? because their densities are different. So how do we calculate density of those gases? So in this question, I'm asking, okay, which one of these has this density? But why don't we just calculate the density of all of these gases? It's not that bad, I promise. When you're given a gas, its identity, and a certain temperature and pressure, and you want to calculate the density, just inspect the units. Any math-based question that you're stuck on the exam, if you don't know where to start, the best place to start is just look at the units. Density has a unit of grams per liter. All right. So liter is, so if I know how much grams of sample I have, and I know how much volume it takes up, I can calculate the volume. So volume, isn't that a component of PV equals nRT? So that's what I'm going to do. I'm going to figure out what the volume of one of the gas samples is to get the denominator. I'll use PV equals nRT. So it's the V component there. The problem is, where do I get grams? We need to make an assumption here. With densities, the best thing to do when trying to calculate the density is assume you start with 1 mole of gas. That's the best thing to do. Just, you need to pick an amount to start with. Because what I'm going to do is ask myself, okay, if I have 1 mole of any one of these gases, let's say helium, and I ask you, how much does 1 mole of helium weigh? What will you tell me? Yeah, your eyes dart to the periodic table and you tell me 2 grams, right? 1 mole of helium weighs 2 grams. Can you tell me how much 1 mole of helium gas takes up in terms of volume? Can you answer me that? It'll take a little bit of math, right? But you can figure it out using PV equals nRT, right? If you know you have 1 mole, that's N. Do you know the pressure? Yeah, it's given. It's 1.31 ATM. I know the pressure. Do you know R? Yes, that's a constant. Do you know temperature? Yes. So with the pressure and temperature given, and the assumption that we're starting with 1 mole, you can calculate volume. So let's just do that. So we're going to assume, okay, 1 mole of gas, how much is that going to take up in terms of volume? This is called the molar volume. All right, so 1 mole times R, I don't feel like writing it out, 303 Kelvin over 1.31 ATM. So 1 mole of gas at these conditions takes up, okay, where's my key? Takes up 18.98 liters. All right, any gas, 1 mole of any of those gases will take up that much volume. All right, so to get density, remember, density is grams per liter. I know the denominator now. Now I just need to calculate, okay, what's the gram amount? And I can calculate density. For all 3 of these, the denominator is going to be the same. But for all 3 of them, will the numerator be the same? Does 1 mole of each of these gases weigh the same? No, they don't. So they're all going to have different densities. So for helium, it's going to be about 2 grams, divided by 19 grams. So that, or sorry, 19 liters. So that clearly is not 2 grams per liter. It's clearly not 2 grams per liter. Or is helium not 2? Is it 4? Okay, just say it. You don't need to whisper. Just yell at me. Yeah, it's 4. But still, is that anywhere close to 2 grams per liter? No, it's not, because that's what we're looking for, 2 grams per liter. All right, how do we get the density of argon? The denominator is still going to be 19 liters or whatever, 18.98, whatever, it's close enough. But now the numerator is what? 39 or whatever, 40. Okay, and then xenon, what would the density of xenon be? 131. Okay, great. Grams over 19 liters. So which of these gases has a density of 2 grams per liter? The argon. Yes, that's how we do it. Okay. So this one's nice, or it's tricky because we actually had to calculate 3 different densities to figure out the answer. But you could do it for any of these. I could just ask you, what's the density of helium at this temperature and pressure, and you go through the same steps. This one's just made a little bit easier, as long as you know that each of the gases, when you have 1 mole of them, will have the same volume. But that's the strategy you want to use. All right, you just assume one mole. Okay. The question is, for converting temperature to Kelvin, is it 230, 273 or 273.15? It is 273.15, but sometimes I'm lazy and I drop the 0.15 because of the sig figs of other things. Tacking on that 0.15 in the end doesn't end up changing the answer that much. But in practice, you should always put the 0.15. That'll give you more accuracy, but sometimes I'm just lazy. Okay. All right. Okay. So let's keep going. Okay, 5. Oxygen gas is generated in a decomposition reaction. So this question number 5 combines stoichiometry from chapter 3, but with gases now. Because now, remember in stoichiometry, in order to use a balanced chemical reaction, we had to be in the unit of moles, right? 3 moles of oxygen requires 2 moles of the potassium, what is that, chlorate? Before in chapter 3, we talked about, we were able to get to moles of, products or reactants using molar mass. I gave you a gram amount. You used molar mass, got your mole amount. But now that we know gases, we have this new fun way to get moles of a gas, that's N. So we just have this new way to get N. So using the information given here, I give you the volume of oxygen, its temperature, its pressure. So with that information, I should be able to get moles of gas, moles of our oxygen gas using PV equals nRT, all right, with that information. But then once you get moles of oxygen, all right, once you get moles of oxygen, you then can use stoichiometry. You can use stoichiometry just like we did in chapter 3. So you would put 3 moles of oxygen on the bottom, 2 moles of the reactant that we want on top, ClO3, and then the molar mass. So 1 mole of potassium chlorate, it weighs something. What is it? 122.55 grams. And then that's how you do it. All right. So just like before in chapter 3, it's just we have a new way to get moles. We use PV equals nRT. All right. Or, I could reword this question. If I gave you grams of reactant, it's the same thing. If I give you grams of reactant, you convert to moles of reactant, figure out, okay, how many moles of oxygen is produced, then plug that N into PV equals nRT, and then calculate a volume or whatever the question's asking. We just have this new way to play with, to use moles. Before it was molar mass to get to grams, or we used molarity and moles to get to volume. Now we have PV equals nRT for gases. So that's fun. Okay. So those were all the math ones. So let's do the not math ones. Yeah. Okay. Quick poll question. Would we prefer a math-based exam or a conceptual exam? Okay. How about raise your hand for math? Okay. Raise your hand for conceptual. Interesting. Okay. So, hey, no, remember, be nice to one another. Be nice. So at least for my class, I went through all the midterm results and I saw that the most, hey guys, let's bring it back. So the most missed problems on the midterms were conceptual questions. I think you guys might discount those on exams. And my best suggestion for those conceptual problems is sometimes you got to turn on your monkey brain and use your intuition. All right. Don't try to overthink it. All right. What I mean by monkey brain, think of attractions when things are attracted towards one another versus repelling from one another. That can help you answer a lot of questions. Okay, so the question is, they're looking at the supplemental information sheet. R will be given to you, but it's probably best to memorize them at this point. Okay, so let's move on to 6. These are conceptual questions. A lot of these have to do with kinetic molecular theory and the idea of, gas particles and the root mean squared velocity of those. It's not super easy to calculate the average velocity of a gas particle of a sample. They're all moving at different speeds, but what we can do is use a root mean squared velocity, which is directly related to temperature. Temperature is something I can measure. I can't really measure an average temperature or average velocity very accurately because we have a Maxwell-Boltzmann distribution of particles. I would actually have to get a histogram in order to do that, and that's kind of difficult to do. But root mean squared velocity still gives us a comparison that we can use to compare different samples. And what's great is that all of the trends are in here, because if we look at this equation, what are the ways that this velocity can increase? 3 is a constant, so that can't change velocity. R is a constant, that can't change velocity. But what about temperature? If temperature goes up, velocity goes up as well. So hotter samples on average are moving, those particles are moving faster. Also, our intuition says that too. What about this, molar mass? What happens if we compare heavy particles to light particles? How does root mean squared velocity change? Light particles move faster, heavy particles move slower. All the trends are in this equation. So what gas possesses the higher root mean squared speed at room temperature? Neon, yes, because it is lighter. At what temperature will oxygen have a faster RMS? 5 or 125 or 125 Celsius? The hot one, yes. Which gas will effuse faster? Effusion is directly related to what? Speed as well, yes. Effusion is actually related to collision rate. Particles collide more if they're moving faster. So let me write that. So root mean squared is proportional to collision rate. I don't know if I spelled that right, which is also proportional to the rate of effusion. So which one will have the faster effusion rate? The heavy one or the light one? Light one, okay. Which gas, so this one's different. Which one possesses the greater density at STP? You should not have to do any calculations because I'm just asking which one's more dense. Which one do you think? Argon. Why the heavier one? Yeah, there's more mass because remember, density is grams per liter. The denominator for both of them will be the same. I don't actually have to calculate it. I just know it's going to be the same because it's the same pressure and temperature, but the gram amount is different. And so argon is heavier than neon. Yes, okay, good. Which gas will deviate more from ideal behavior at high pressures? What do we think? So at high pressures, which term, so remember our van der Waals equation. We have this A term and the B term. So the A term is related to what? Attractions. B is related to size. So at high pressures, size matters because in order to get high pressures, think you have like a small volume, you have a small volume and you have to shove a bunch of particles in a small volume, tons of them, right? To get a high pressure. If you shove a ton of particles in a small volume, there's so many particles, they start to take up space. All right, and that's when their size starts to matter. So basically this question is asking, okay, which one has the higher B term, the higher B size, because B dominates at high pressures. So which one's bigger? And so in this case, it's argon is bigger. Yes. Okay. And then on the other hand, which gas will have the larger A term in the van der Waals equation? N2 or CO? CO, yes. And because A refers to attractions, these particles, remember one of the tenets of kinetic molecular theory, we make the assumption that the particles are not attracted towards one another, that basically they're billiard balls that are just bouncing off one another, purely elastic collision, no energy loss. But we know that molecules actually don't have no attractions. Some of them do have attractions. And so CO, because it's a polar molecule, is going to exhibit more attractions than the non-polar molecule. And so we'll see that there are appreciable attractions in a CO sample. All right. Okay, great. Okay, yeah.
So I've noticed the symbols for RMS have changed. Like on the reference sheet, it's like a B. I'm pretty sure it's a Greek letter, and then here you use mu, and I've seen mu as micro. Which one is it?
I don't know. I use mu. I might be wrong. I might be wrong. But the RMS part is the important thing. I'm not sure what the convention of the if the textbook uses new, it's like a fancy V. It might be new. I don't know what it is. Is it? I have to look at the book. I might be wrong. It does not matter. Okay, good. All right, so on that same vein. Okay, that was chapter 10. How about 11? All right, so which of these substances has the higher normal boiling point? What is this question actually asking? More IMF. So let's quickly go through all the IMFs. The first one, LDF. The second one, dipole-dipole. The third one, hydrogen bonding. The fourth one, ion dipole. But that one is weird. That one like doesn't fit in the rest of it. Ion dipole, we only use ion dipole when we have a salt, like a salt dissolved in water. All right, so we don't typically care about ion dipole, especially in these questions, these ones, because these are all molecules. So we'll never consider ion dipole, but we will consider the first three. So LDF, we look at molar mass or surface area of our compounds. It's most important in nonpolar compounds. For dipole-dipole, we are looking for a permanent dipole in our molecules, so polar molecules. Molecules that are overall polar. And then finally, hydrogen bonding, you're specifically looking for a hydrogen attached to a electronegative atom with a lone pair on it. So like an oxygen with a lone pair, a nitrogen with a lone pair, or fluorine with a lone pair. So the hydrogen has to be directly connected to those things. Those are the types of samples that have those groups, those functional groups, will exhibit hydrogen bonding. It can't just be a hydrogen anywhere. The fluorine can't just be anywhere. It has to be directly connected to a hydrogen. Okay, so let's look at these things. So basically, we look on this list, we find, okay, what's the strongest IMF? If there's more present, you're going to see a higher boiling point. So let's look at the first one. What's the strongest IMF in this compound right here? For the first one. Hydrogen bonding, it's right there. All right, what about the second one? There's also hydrogen bonding, but what's the subtle difference? There's two of them. So because there's two hydrogen bonding, and hydrogen bonding is the strongest of all three, and that's the biggest difference, that one's going to have the highest boiling point. So because let's think of it, IMFs is attractions. The more your liquid particles are attracted to one another, if they're really attracted to one another, is it going to be hard to send them into the gas phase? Yeah, it's going to be real hard. So you're going to see a higher boiling point temperature. You're going to see a higher enthalpy of vaporization. All right. So a lot of these concepts are connected to one another. They all stem from IMFs. All right, the next one, Br2 ICl. Which one has the higher boiling point? ICl. Why? It's polar. Yeah. Yeah. Wait, this one? This first one only has one. Well, actually, it does have two spots to hydrogen bond, but it's identical over here. So actually, yes, technically this has four. Yeah, 4 electropositive hydrogens. Yeah, but we can see it just has double the amount. Yeah, okay. All right. Yeah, so ICl is the polar one, so it's going to be have the higher boiling point. All right, pH3 or SaH3? What do we think? Maybe drawing it would be useful. Yeah, okay, so let's draw it. So pH3 or ASH3. So The strongest IMF present in these would be what? Dipole, dipole. So it looks like they're both polar, but can you tell which one's more polar? I can't. I don't know. I just know that they're both polar. So let's think about how they are different. So let's move back up. Let's back up a little bit. Let's compare their LDFs instead. So which one's heavier? The arsenic one. So yeah, that's going to be the one that has more IMFs, has a higher boiling point. Okay. All right, so for number 8, let's do this one. So 8 is actually exactly the same as 7. We're doing the same strategy. We're inspecting IMFs, but now we're tracking something different. We're looking at vapor pressure. Vapor pressure. I think this concept folks don't understand. So let me explain to you my analogy. That helps a lot. Yeah? Oh yeah, both of the compounds are polar. I can't tell which one's more polar. They both have the exact molecular geometries, right? They're both like trigonal pyramid. I can't tell which one's more polar, so I'm going to go to the next IMF that's weaker, and that's London dispersion, and we compare molar masses. So AsH3 is much heavier than phosphorus, so that's why. Okay, yeah. All right, vapor pressure. Folks have a lot of trouble with vapor pressure. It's hard to think, oh, if I have a glass of water, right? H2O, it's a liquid. It's hard to imagine there's actually some water gas particles above the liquid. That's a hard thing to wrap our heads around, that it's not just the liquid, it's actually a liquid in a gas at equilibrium, because all liquids exert a vapor pressure, all of them. Some of them more than others. So I'm going to tell you the trend first. As IMFs increase, vapor pressure actually decreases. And let me explain why. Okay, well, let me explain vapor pressure, because again, a lot of people can't wrap their heads around it. So I use this analogy. Relate vapor pressure and volatility. Those mean the same thing. If something exerts a high vapor pressure, typically we call it volatile. Volatile things typically smell bad. So think about nail polish remover. Ooh, do you think that has a low vapor pressure or a high vapor pressure? High, because what are you smelling? Is the liquid entering your nose when you smell nail polish remover? No, it's the gas particles. But if you just have a cup of nail polish remover, it's a liquid. How do I smell it? It's because some of those liquid particles have enough energy to escape the liquid, right? They're letting some of their friends go and they're entering your nose. So things that smell exert high vapor pressures. Because I like to think the particles, okay, all liquids, their particles are attracted towards one another. They're hugging one another. All right, so if you're in a liquid and you're hugging all of your liquid particle friends really tightly, are you gonna let any of your particles enter the gas phase? If you have really high IMFs, if you have really high attractions, are you gonna let your friends go? No, you're not. But what if you have really weak IMFs? What if you don't like your friends that much? You don't hold on to them. Are you going to let your friends go to the gas phase? Yes, you are. So that's going to be a high vapor pressure. So low IMFs, high vapor pressure. Low IMFs, high vapor pressure, high IMFs, low vapor pressure. Okay, got it? And then one other thing that changes vapor pressure is what? Temperature. And you know this too. Can you in your head imagine what vinegar smells like? Okay, now I'll put it in the microwave for 30 seconds and then take it out. Did you do that? Okay, how did the smell change? It got worse. So how did the vapor pressure change? It increased. Okay, so how does temperature relate to vapor pressure? It increases, yes. So as temperature increases, vapor pressure increases. Yes, but let's think about it on a energy particle diagram. Okay, all you and your friends, you're all particles in your liquid party. You're all hugging one another. You're all attracted to one another. But then you start turning up the heat. You give it a lot of kinetic energy, all right? So you increase the heat, kinetic energy increases, you start wiggling, moving faster. If you're moving faster, but you're still attracted to your friends, you're going to let more of your friends go out into the gas phase because you're all wiggling. You're all wiggling so much that you're not holding on to one another as tightly anymore, right? And that's why things boil. When we heat things up, we increase the vapor pressure of the liquid to a point where vapor pressure equals external pressure. And now all of the liquid particles enter the gas phase. That's when something boils, when your vapor pressure of your liquid equals the external pressure. Okay, now you understand vapor pressure? Yes, okay, good. Does water smell like anything? So does water have a high vapor pressure at room temperature? No, it doesn't. Think about the IMFs in water. It's hydrogen, 2 hydrogen bonds, right? It has really high hydrogen bonding, really high IMFs. So it's going to have a low vapor pressure and a high boiling point, and we see that. My trick doesn't work for everything. It doesn't work for everything, but some of the examples I show, it does, but it doesn't work for everything. Okay, so for number 8, it says, which of these substances has the highest vapor pressure at room temperature? What is this question actually asking? Lowest IMFs, that's it. That's it. Okay. So which one has the lower IMF? The lighter one, because both of them are nonpolar. What about B? Which one has lower IMFs? The first one, because this one is polar, but the first one is not polar. All right. Okay. And the last one, H2O and H2S. H2S, yeah, because H2S, both of them are polar, but water can hydrogen bond. Can H2S hydrogen bond? No, it cannot. But Dr.N, it has a lone pair on it. Why can't it hydrogen bond? Because it's sulfur. Sulfur is not that electronegative. Yeah, we want to look for O, N, or F. Okay, cool. Not that bad, right? Okay. Which substance will exert the highest vapor pressure at their respective normal boiling points? What does normal boiling point mean? Where? Okay, so the normal boiling point, yes, it's when a liquid becomes a gas. But what's the point of normal? Why did I say normal? Yeah, at 1 atm. I like to say on Earth. On Earth. On Earth, water boils at 100 degrees Celsius. Yes. But if your instructor showed on the bench top here, when we used a vacuum pump, we were able to get water to boil at room temperature, right? Yeah. So there's many ways we can make a water boil. So normal boiling point means that the boiling point on Earth at 1 atm. 1 atm is important here because it's when the vapor pressure of all of these liquids equal 1 atm. So the correct answer is D. Is D. All of them at their boiling points have a vapor pressure of 1 atm because that's where they exceed external pressures being exerted on it. That we've exceeded those particles, those liquid particles have overcome the external pressure on it. It just so happens that happens at different temperatures for each of these substances. For water, it happens at 100 degrees Celsius. For ethane, it happens really, really low, at a really low temperature, right, where it boils. And at, what is this, ethanol, again, it happens at a really low temperature as well, lower temperature than 100 degrees. But the main thing is that all of these will boil at 100 degrees, or all of these will boil when their vapor pressure is equal external. Okay, cool. All right, let's keep going. All right. Okay, I'm done with 11. Let's do 12. Let's arrange these substances in increasing normal melting point. So this is related to solids. All right, when we think about ionic substances and their melting points, all right, we just look at lattice energy. That's something we already know. Ionic compounds have really high melting points. But are there only ionic compounds on this list? No. There's some ionic. There's like these, those, okay? But then how do we handle these? How do we know the melting points of these guys? What are these? These are molecules. So these substances will adopt what type of solid structure? It's not going to be, what are the 4 types of crystalline solids? Metallic, ionic, network covalent, and molecular. So here are our ionic guys. I know I'm going to look at lattice energy, but how am I going to handle these ones? These are molecular. So when we melt molecular compounds, what do we break? IMFs. So we just look at IMFs. So, but of these, if we compare molecular compounds and ionic compounds, which ones have higher melting points? Ionic, yeah. So we have basically 2 different trends. We're gonna place our molecular compounds first. Those are gonna have the lowest melting points. Then we're gonna place our ionic guys. They're gonna have the highest melting points. Okay. For ionic, we're gonna look at lattice energy and trend them that way. For molecular, we're going to look at IMFs. Right. Okay. So let's do the moleculars first. So I'm going to ask you, you have a solid sample of methane or you have a solid sample of methanol. Which one is harder to melt? Methanol, yes, because there's hydrogen bonding. So simply, it's going to be CH4 and then the other one, CH3OH. Great. Okay. Okay, now we do the ionic ones. They are going to be even higher. They're going to be much, much higher. All right. But when I throw in those molecular ones, students get like, they freak out. Because they're like, methane doesn't have Q1, Q2. How can I figure it out? We can't consider Q1, Q2 for all of them. So for the ionic ones, we do consider Q1, Q2 because we're essentially just looking at lattice energy. When we melt an ionic substance, it's related to the attractions of the lattice energy. So we do the exact same trends here. We look at Q1, Q2 product. We look at D, the size of the ions, if they're the same size. So of these, which of the ionic compounds are hardest to melt? The strontium, yeah, because it's +2, -2. So strontium is the highest. Then we have lithium fluoride, lithium bromide. They both have +1, -1 products. So their Q1, Q2 are the same. So we look at D instead, size. So which of those has the higher melting point? The fluoride or the bromide? The fluoride, yeah, because it's smaller. Basically, because the ions are smaller, they pack together more, so it's going to be harder to pull them apart to melt. Okay, so it's going to be the fluoride and then the bromide. Good. All right. So 2 things you need to know: that ionic compounds have higher melting points than molecular compounds or solids. Molecular solids have the lowest melting points. Of the ionic, to trend melting points, you look at lattice energy. We already know how to do that. For molecular, you look at, typically you look at IMFs, just like we did for boiling points. Okay, cool. All right, next one, 13. We have the electrical conductivity of a white soft solid is studied, and it's found to be highly insulating. When it's added to pure water, it dissolves completely, so it's highly soluble, but it does not conduct electricity. Which is the substance? Is it a molecular solid, a weak electrolyte, an ionic solid, metallic, or we can't figure it out? What do we think? Yeah, it is a molecular solid. Yeah. Yeah. Look at your notes. Yeah, just look at your notes. Yes. So where are we now? Yeah, so 13. We know it's a molecular solid because of what are the basically the big traits here that point that it's a molecular solid. Soft. I mean, it dissolves in water, but there's other things that dissolve in water too. There we go. Yeah. So let's break this down. So if we think about dissolves in water, it dissolves in water. Molecular compounds do that, like sugar. Sugar is molecular. It dissolves in water. But sugar doesn't conduct electricity because there are no ions present. Salt also dissolves in water, But the difference is it dissolves in water, but it does, salt water does conduct electricity. Okay, there we go. And then, but for me, I think it's the soft component. Molecular solids are always very soft. Metallic substances, ionic substances, they're typically really hard. Network covalent, also hard. Ionic is brittle. It's brittle. Yeah, let's look at, if we think about conductivity. All right, conductivity of the solids, only metallic solids will conduct in their solid phase. Some people will accidentally think, oh, but NaCl solid, that has ions, that conducts electricity, but that's actually not true. Ionic solids that are in the solid phase, their ions aren't freely moving around. So they do not conduct electricity in the solid phase. But how can you get NaCl to conduct electricity? Dissolve it in water, yes. Yeah, so metals do conduct in their solid phase because of, we use the sea of electron idea, those delocalized electrons, really low ionization energies to relate to that. Okay, there we go. All right. All right, so 14, and then we'll be done with 12, I think. And then we'll do old stuff. I haven't even been drinking my LaCroix. So this is like the last learning objective for chapter 12. Let's look at this unit cell. So this is the simplest repeating unit within a solid. I try to give you the different atom colors to represent different elements here. It's A, B. All right, A is the purple atom, B is the pink atom. I want to know, what is the formula unit? What is the empirical formula for the this compound? So our strategy here is we need to figure out how many pink atoms, how many purple atoms are inside the unit cell. If we know that, then we can get the ratio of A and B, and we can get the simplest ratio, the empirical formula. So I like to go do this one at a time. Do you want to do the purple atoms first or the pink atoms first? Purple, yeah, they're easy. All right, so let's look at the purple. We need to inspect the crystal structure and think, okay, where are those purple atoms and how much of each atom is inside the box? Where are the purple atoms? They're inside, and then how many are there? 4, yeah, so there's 4 purple atoms, they're all inside. So total, how many are inside the box? 4, okay, great. Now let's do the pink. Oh, they're both P's, purple. Okay, so wait, purple is what, A? Okay, so 4 A atoms. So now let's do the pink atoms. All right, so that's B. So I take it one at a time. I look at one location. So for me, I'm gonna look at the corners first. All right, and then let's count how many total identical atoms, pink atoms are in the corners. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, so there's 8 B atoms. Yeah, B is pink. On the corners, how much of an atom is actually inside the box when it's on a corner? An 1/8, yeah. So total, there is 1 B atom just coming from the corners. Did we take inventory of all the B atoms? No. Okay, we got to do the other ones. Now these B atoms are on the face. How many? 6. 6 B's on the face. How much do we count if it's on the face? 1/2. All right, so there's another 3 B atoms. Okay, great. So we see that there's 4 A's and a total of 4 B's. So what? So we can write the formula A4B4. But is that an ionic compound that you've ever seen before? No, we typically simplify it. So simply the formula unit or the empirical formula is just going to be AB. Okay, but how I got from A4B4 to AB, that tells me actually, that thought process tells me how many formula units are inside the unit cell. That's the next question. What was the multiplier I used? 4, yeah, and so that means that there are 4 ABs inside that unit cell. Whatever I use to like simplify it, okay? All right, and a way I could elevate this question as a multiple choice is I could say, I could give you the same thing. I would give you this same picture and I would say, which of these compounds could adopt this crystal structure? Sodium oxide or calcium chloride or I don't know, strong, no, I don't want that. I want fine, lithium fluoride. A, B, C. Okay. B, C. C, yes. So to elevate this question, I didn't ask what is the empirical formula. I want you to relate it to an actual formula given a chemical name. So this is kind of review of chapter 2 stuff, naming. From these names, you should be able to get the chemical formula. So we need to know charges. Sodium is Na+, but oxide is O2-. So the balanced chemical formula would be Na2 oxygen. Is that the correct empirical formula? No. Calcium chloride is CaCl2, so no. And so the only one would be lithium fluoride, so it would be that one. Yeah, so that's how we could elevate it. All right. Okay. So I'm going to be done with chapters 10 through 12. So that's an hour. So let's use this last hour to do other chapters. Give me a question number or a chapter. 17. 17. Okay. Oh, that's hot. Okay. All right, 17, chapter 1 stuff. It's unit conversion. So you just got to be real careful with your units and your conversions here. I have a volume of a room, the mass of air in the room. What is the density of air in milliliters or grams per milliliter? So my goal here is I need to get the gram amount or the mass amount in grams, and I need to get the volume in milliliters. But the problem is, was mass given in grams? No. Was it given in milliliters? No. So I need to convert meters cubed to milliliters. So somehow I need to do that. And I need to convert kilograms to grams. That one seems easy, right? Okay, so let's do the easy one first. Let's convert kilograms to grams. So 44.8 kilograms. How many grams are in a kilogram? 1,000. Do I put the 1,000 on the bottom or on the top? Top, yes, because right now kilogram is in the numerator. So I want kilogram in the denominator to cancel it. I know that 1 kilogram is 1,000 grams. And so the units cancel, I get grams. So this is 44.8 times 10 to the 3 grams. So this is the number that's going to go in the top of my density calculation. All right. Now I just need to do the hard one, the denominator milliliters, and that's this meters cubed business. Because I have a problem. Meters cubed looks nothing like a milliliter. How the heck do I relate that? There is one conversion you absolutely need to memorize. 1 milliliter equals what? 1 centimeter cubed. So if I can get meters cubed into centimeters cubed, then I'm home free. I could even go to liters if I wanted to, right? Okay, but the problem is, do you know how many cubic centimeters are in a cubic meter? I don't, but do you know how many centimeters are in a meter? Yes, I do. Okay, great. So 1 meter is how many centimeters? 100. Okay, so you basically have to do this 3 times, because what is a cubic a cubic meter. It's a meter times a meter times a meter. So all you have to do is this conversion 3 times. So you just have to do this. All right, that's it. That's it. And so now if you finished right now, your unit would be in cubic centimeters. All right. And so then you can use this last conversion. 1 cubic centimeter is 1 milliliter. 1 milliliter. There's your answer. So how I would put this into my calculator, I just want you to be positive here. This cubed is applied to that 100. That cubed is applied to that 1. So how I would put this in my calculator is 38 times 100 cubed. That's what I would put in my calculator. Because 1 cubed is what? 1. So you don't need to put that in. All right. So 100 cubed. So I don't know what that is. Oh, wait, I have my key. Where is it? I don't know. It's something. 3.8 times 10 to the 7 milliliters. Okay. So there's my denominator. There's my numerator. Just do the math. How many sig fig should my answer have? 3. Because everything's multiplication and division. Both of them start with 3. Okay. All right, let's keep going. All right, is there another question from chapter 1 that someone wants to do? 18? Let's just quickly just talk about 18. It's about accuracy and precision. Accuracy, what do you compare when you try to determine whether something's accurate? The true value. And typically you're comparing that to the average. Which one has an average closest to the true value? What if you don't know the true value? Can you say anything about accuracy? No, you can't. All right. What about precision? What do we look at precision? We look at the range, the high and the low of the data points. Whoever has the narrowest range is the most precise. They could be way off. All right. They might not be accurate, but they can be precise. All right. So they're not mutually exclusive. All right. All right. All right. We did 18. Okay. Does someone have a question? A number from chapter 1 or 2 or 3? Just tell me when to stop. 23. Okay, yeah. What is the empirical formula of a compound that contains 81% fluorine and 14% carbon by mass? So with these questions, the empirical formula questions, the big idea is you need to figure out how many moles of each element you have. Once you have the number of moles of each element, you divide by the smallest number. That's how you get your empirical formula, your mole ratio. Same thing if this was combustion analysis. You just find moles of each element. But with this particular question, it's a percent composition. There's a little trick here because we're given percentages. What's a good assumption to make right off the bat? 100 grams, because if we have a 100-gram sample, how much of that sample is fluorine? 81 grams fluorine, 19 grams carbon. From that information, you should easily be able to get moles of each. And that's how you get the mole ratio. So with carbon, it's you divide by 12.01 grams, 1 mole equals something. Fluorine, you divide by 19, I don't know, 19. Yeah. 19 grams, 1 mole fluorine. So you get, there's 4.26 moles of fluorine. You have 1.58 moles of carbon. So does that mean that my formula, should I round carbon up to 2 and fluorine down to 4? So it's C2F4? That sounds right. No, we don't do that. What do we have to do with these numbers? Divide by the smallest one. Yes, by doing that, we basically force one of them to be a whole number. So if we divide both of them by 1.58, all right, we force carbon to be 1 mole of carbon. And then fluorine is 2.696 moles of fluorine. So do I just round this up to 3? And so it's CF3. No, what do I do? Yeah, I need to multiply by some number to get rid of that fraction. So I just squint my eyes and think, okay, 0.69, that's really close to 0.66, which is 2/3. So if I multiply by 3, I can get rid of that. And so what I mean by multiply by 3, we multiply both of them by 3. All right, so 2.69 times 3 is 8. And 1 times 3 is 3. So there's 3 carbons and 8 fluorines, so it's C3F8. Okay, it's propane, but all of the hydrogens are replaced with fluorines instead. All right. All right, next question. 35. I'm going to back it up to 33 and we'll work our way there. Okay. So this is chapter 7 stuff. So our periodic trends, Z effective, ionization energy, those things. So here for 33, I'm asking tin has 55 electrons, neutral tin. And it has 55 protons, right? Or 50 protons, yeah, 50 protons, 50 electrons. Electrons in which subshell will experience the highest effective nuclear charge? So what is effective nuclear charge? Z minus S, yes, shielding. So for all of these electrons, all of them are on a tin atom. So all of them have Z is the same as plus 50 for all of them, right? All of them are attracted to a positive 50 nucleus. But what is different for these electrons? Shielding. How do we calculate shielding? What is shielding? It's all the electrons in front of it. So all of the electrons in n-1 energy levels, essentially between that electron of interest and the nucleus. All right. So when we look at a 5p electron, we count all of the electrons at n equals 1 all the way to n equals 4. When we count 5s electrons, if we're a 5s electron, what electrons are shielding us? All of the electrons in n equals 1 until 4. What about a 4s? 1 till 3, 3s, 1 until 2, 4p, 1 until 3. Yeah, so which one has the highest Z effective? Which one is the most attracted to the nucleus? 3s, yes, because the shielding is the lowest for that one. That it has the least number of electrons shielding it. So if Z effect, or if a 3s electron has the highest experiences the highest effective nuclear charge, shouldn't it be the most attracted to the nucleus? Yes. So let me reword this question. Which electron is closest to the nucleus? 3s, right? Because it's n equals 3. It experiences the most attraction, right? It's most attracted to the nucleus. It's going to be closest to the nucleus. Okay. Right. All right. Yes, there we go. All right. So let's do all of these because they all, to me, they're all basically the same question. So with all of these trends, when we think about size, ionization energy, electron affinity, students will show me, they'll show me their periodic table with the trends written. They'll draw the trends written. They'll be like, is this right? And I'm like, I don't know, because I don't think about trends in terms of the periodic table. We always consider 3 things when looking at trends. We look at n value of the electron. We look at the Z effective that's experienced by that electron, or sometimes we consider electron repulsions. If it's an ion, if it's a cation, anion or something, right? They all stem from the same things. So me personally, I don't look at the periodic table. I don't draw the arrows because I don't like to memorize things. I like just to think, okay, if if I wanted to rip an electron off an atom, it's going to be easier if that electron is further away from the nucleus. So larger atoms, it's easier to just pop off an electron. All right. So let's go through these. Larger atom of the following pair. And for what reason? Iron 2+ or iron 3+? 2+. Why? Because it has more electrons. Yeah, so basically it's that third reason. Electron repulsions. Okay, oxygen 2- or sodium plus. I will point out one additional caveat. Sometimes we need to have our eye out for isoelectronic species. Yeah, isoelectronic, meaning they have the same number of electrons. So we typically just look at the number of protons, and that will tell us which one is larger or smaller, because oxygen 2- and sodium plus, if we look at our periodic table, they both have the same electron configuration. They both have 10 electrons. Okay, so we have 10 electrons. So to me, I don't know which one, is bigger or smaller. It's 10 electrons for each. So we look at where they do differ. They differ in their number of protons because the elements are different. So oxygen has how many protons? 8. Okay, and then sodium is +11. Right? So if you are a dumb electron, are you attracted to +8 or +11? +11. So which one's bigger? Oxygen, the oxygen one, because the electrons are less attracted to +8, right? Same number of electrons, 10 electrons attracted to a lesser positive nuclei. All right. All right, last one, potassium and bromine. Which one's larger? Bromine? It's straight up potassium. Yeah. So this one's tricky because you might look at it and be like, okay, potassium's 19, bromine's 35. Wow, that's so much heavier. Bromine has to be bigger. It's not. It's not. Because the trends left to right across the periodic table, it actually has nothing to do with mass. It has to do with what? Z effective. Z effective increases left to right. So the radii left to right across the periodic table actually decrease. Yes. Because what we see here, these trends, as N increases, size increases. As Z effective increases, size what? Decreases. Again, we're just electrons. If we're more attracted to something, we're going to be closer to it. So the size is going to decrease. Yeah, so potassium is actually bigger because the N values are the same, right? They're N = 4. But it's the Z effectives that are different. Potassium is what? +1. Bromine is +7. If you were an electron, what are you more attracted towards? +7. So you're going to be smaller in bromine. Yeah, okay. Which is weird because it's so much heavier. That is weird. Counterintuitive. Okay. All right. So for these same ideas, think N, Z effective, electron repulsions in terms of these, which atom possesses the larger ionization energy? We're basically asking which of these compounds or atoms is the electron harder to remove? An electron is going to be hard to remove if it's close to the nucleus, right? If it's close. Right, it's real close to that positive charge, or if it's really attracted to that nucleus. So we're going to look at like N and Z effective. We're going to look at both of those things again. We're looking at all the same stuff. Okay, so K and Br, which one is it harder to remove the electron? Bromine, because it's smaller. Yay. All right, calcium and calcium plus, which one's harder to remove an electron? The plus, because cations are always smaller. Yeah. Okay, then I'm just wrong. Just wrong. Yeah. But yeah, bromine is, yeah, it's smaller. So yeah. Yes. Is it just that one? Oh, I probably in my mind, in my mind, I probably just thought easier. Yeah, I don't know. Sorry. Okay, do I have a reason written? Okay, so you understand, right? You understand, right? I circled the ones that were easier to remove. Very good. All right. Okay. Okay, again, which ones are harder to remove? Chlorine or chloride? The neutral one or the anion? Yeah, chlorine. Again, because it's smaller. Yes, it's smaller. All right, last one, phosphorus or arsenic? Phosphorus. And this reason, because it's smaller, but for what reason? N value. Okay. So do you need to memorize memorize it? Not really, not really. Okay. All right. Which ones possess the most negative electron affinity? Most favorable. Which of them? So this question is essentially asking, when you add an electron, when the electron is really attracted to the nucleus, to that atom, it's typically going to be very favorable. And it's going to be a really exothermic reaction. You add that electron, it's really attracted. You'll get a exothermic reaction. So again, we're going to look at N value and Z effective. If you bring the electron closer to the nucleus, it's more favorable because nucleus is positively charged. If you put a added electron on something with a high Z effective, again, that's going to be very favorable. All right, so chlorine and bromine, which one's more favorable to slap on an electron? It's chlorine because it's smaller, yes. Because it's smaller. When you add an electron, it's going to be closer to the nucleus. They both have a +7 Z effective, so there's no difference there, but the N values are different. And chlorine is 3 and bromine's 4, so you're adding the electron closer to chlorine, so it's going to be more favorable. Aluminum or phosphorus? Phosphorus, because it's smaller, or because look at its Z effective as well. Aluminum's +3, phosphorus is +5. Are you more attracted to if you're an electron, are you attracted to a 3 or a 5? A 5. So you're going to release more energy once you grab onto that +5. Okay. Chlorine, or the chlorine anion or the chlorine cation, which one are you more which one's more exothermic, the electron affinity? Which one? The anion or the cation? Yeah, the cation. Yeah. Yes, fluorine is an exception. Yes. Good. All right, what's next? All right. Okay, all right. So 37. Y'all whisper like this is the end of the world for this question. I like this question. It's like geometry. Because this question could be made a lot harder. I could give you the actual kilogram per mole, thermodynamic values for forming an ionic compound, but I don't. I give you each step. I give you each step of the Born-Haber cycle. I tell you exactly how big every arrow is. So we just need to report how big is this last step, this lattice energy step, and make sure we report the positive value. That's it. So yeah, it could be much harder. So a question often that's asked, they'll, if you look at one of these steps, like, okay, so like this step, all right, we're taking, this is the electron affinity of the X atom, but see how there's 2 X atoms? So we actually are taking into account 2 electron affinities of X, But the idea here is if I gave you thermodynamic data, then yes, you would have to take into account the stoichiometry, multiply the electron affinity of X times 2. But I didn't give you thermodynamic data. I literally gave you how much each step costs energy wise. So use these energies as written. You don't have to double anything. You don't have to do any of that. All right. You know, at least for my class, I assigned mastering homework, mastering chemistry questions that did use thermodynamic data, but those are much harder. They're much harder. This is not too bad. So basically what I recognize, which one of these steps is the heat of formation? Heat of formation of mx squared. The 7th, this one. This is basically, it's like the base of the reaction of this Born-Haber cycle, the very bottom, the downward arrow, that's your formation reaction. So I like to reference myself there because I like to say that this step, that's like what I'm focusing on. But I'm just going to take a different route to get there. I'm going to take elements in their most stable state. I'm going to make the salt, but I'm just going to take a different route. So what basically, how to put this together is you say that first formation step is equal to the sum of all of the steps until you get here. The very last step. What is the very last step of the Born-Haber cycle? It's the lattice energy. So you need to add up all of the steps. So delta H1 plus 2 all the way to delta H of 5. So get all the way to this step where we have the ions in the gas phase, and then you subtract lattice energy. That's it. So to answer this question, you just put in the numbers. So in this case, we're calculating delta H 6. So the absolute value of this step is equal to lattice energy. So it's just the magnitude of that arrow. So to put this together, it's negative 690 equals 188 plus 265 plus 620 plus 120 or 1,240. The next step is a negative value. What do I put next? Do I do anything special to it? No, you just add it as is. Add it as is. So it's minus 890 and then minus that lattice energy. And then all you have to do is solve for that. That's it. That's it. And so just imagine if you were given like a different step. If I told you like, okay, the lattice energy is like 2000 kilojoules or something. And I said, okay, calculate delta H3, the third step. You could do that too, right? You just put together the same equation, you just have a different variable. Okay. So these questions, yeah, it's a little bit more daunting. We actually have to put in a number. But the easier way to assess, the other way to assess these questions is looking at relative lattice energy, where, you know, I compare like MgO, MgCl2, and like MgF2 or something like that. And I ask, you know, which one has the highest lattice energy? Which one would you say? MgO, yes. But when I ask that question, which one has the greatest lattice energy, recognize that lattice energy, it's how big this last step is. Okay, so when we make MgO, we have to worry about the second ionization energy, or sorry, second electron affinity of oxygen, which is a endothermic step. So that's what makes this last lattice energy step larger. All right, so all of those things we look at, Q1, Q2, and size, all of those trends is what makes this lattice energy step larger at the end. So when you do Q1, Q2 over D, you're actually making the Born-Haber cycle, I promise. All right, next one. Oh yeah, here's a good question. Which metal, non-metal combination is most likely to adopt that Born-Haber cycle? Which one? So look at the solid. Which one? See? Okay. Do you see how I got that? Basically, I just looked at what element would adopt that ratio of atoms. Yeah, so I'm looking for Mg2 plus and Cl minus. Will give us that ratio. Oh wait, no, actually no, I lied. Whoops. Okay. B and C actually have that same ratio. I didn't look as close. Sorry. Both of them, right? MgI2 and MgCl2. Crap. How can I differentiate them? Look at the other parts of the Born-Haber cycle. All right. Yes, the atom ratio is a metal and two nonmetals. Both of those fit that, but let's look at the other parts of the Born-Haber cycle. What's the state of X squared? It's a gas. So now can you differentiate them? Which one is it? C or B? It has to be C because the most stable state of chlorine is a gas. The most stable state of iodine is a solid. Yes. So would the Born-Haber cycle for MgI involve the sublimation of, or sorry, what is this? Yeah, it wouldn't involve X squared gas. It would involve X squared solid. Yeah. So there's the small detail. All right. All right, what's next? What number? 30 or 34? Okay. All right, so 30, highly exothermic thermite reactions. We have aluminum reacting with alumina iron oxide to form elemental iron and aluminum oxide. Here's the thermochemical equation. This reaction happens and the enthalpy for every mole, every turnover of this reaction, 850 kilojoules of energy is released, meaning that what kind of reaction is this? Exothermic energy is released. All right, so here I'm asking what mass of iron is in grams is formed when 725 kilograms of heat is released. So the great thing about thermochemical equations is it works exactly like stoichiometry. So remember how we said, okay, 2 moles of iron requires 2 moles of aluminum to react. We said that in chapter 3, right? 2 moles, 2 moles. All right, so the difference in chapter 5, where we talk about thermochemical equations, it's the same thing, but now involves energy. 2 moles of iron, if that forms, will release 850 kilojoules of energy. That's it. So we just have this new stoichiometry relationship. 2 moles of iron equals 850 kilojoules of energy released. Basically, I just removed the negative sign because the negative sign just tells us what direction energy is going. And I'm still signifying that by saying energy is released in this case. So what I'm going to do is look at what's given, 725. We are given energy, so we're just going to work backwards, use stoichiometry and get iron that we need. So 725 kilojoules times 850 is going to go on the bottom. 2 moles of iron is up top. All right, am I done? No, I want mass. So I need to do what? Molar mass. Yeah, just like always. All right, and so molar mass, 1 mole of iron is, I don't know, something. And then there's your answer. Okay, whatever. Good? All right. Okay, other 30, any other questions? What's yours? 29, yeah, let's do that because it's right up here. All right. So still enthalpy. Let's use Hess's law to calculate the enthalpy change for this. So this is the target reaction. And so we just need to manipulate the given reactions to get that target reaction. So I like to focus on one reactant at a time. So let's look at this WO3 solid. Look at reaction 1. I have that substance, but is it on the right side? No. So what do? Yeah, multiply it by -1, that flips the reaction. Is it in the right number? No, so what do? Divided by 2. So whatever I do to the reaction, I also have to do to the delta H, okay. So then the next piece here, I'm gonna focus on, look at this other reaction. So there's 2 ways you can do this. You can either focus on hydrogen, or you can focus on water. I'm just gonna focus on water. All right, is water on the right side? Yes. Is it in the right number? No. So I'm going to, this one's a little bit tricky because I already have 2 of them, but I need 3 of them. So I'm going to multiply by 3 halves. All right, that'll get me 3 of them. So you can go ahead and like carry over these things across the coefficients and add them up and prove it to yourself that you get the target reaction, but I don't feel like doing that. But if you have time to kill on the exam and like you can do that, then please do it. But according to Hess's law, we should get these things. So with those delta H values, we're going to be adding up a positive 1685.4 over 2, whatever that number is, and then we're going to add a negative 477.84, but we need to multiply that by 3 halves. So add those 2 numbers together, and then you should have your answer. Hopefully that's what I did. Yeah. Okay. All right, other questions? Yeah. What number? Okay. Yes. Okay. 44. Consider this molecule. What's the hybridization of each of the carbon atoms? So remember my trick here for hybridization. The number of electron domains around your central atom is equal to the number of atomic orbitals you need to combine is equal to the number of hybrids you get out. So, and when you think about atomic orbitals, when you pick them, what you have to choose from is an S, and then a P, and then a P, and then a P. That's what you have to choose from. And you just work left to right. Okay, so this first carbon, how many electron domains? 2. So how many atomic orbitals are we going to combine? 2. And then how many hybrid orbitals do we get out? 2. So what's the name of that hybridization? SP, because we combined an S orbital and a P orbital. So we call it SP. Great. All right, so when you draw the hybrid orbital boxes that are degenerate, how many hybrid orbitals do you draw next to each other? 2. When with this carbon that we just identified, how many unhybridized p orbitals are on that carbon? 1, 2. Let's look at it. How many atomic orbitals did we combine here from what we had to choose from? 2. How many p orbitals did we not touch? 2. So there's 2 unhybridized p orbitals on that carbon atom. So here's another question. If we have an sp hybridized carbon, how many pi interactions can an sp hybridized carbon make? 2, because there are 2 unhybridized p orbitals. Pi interactions happen between unhybridized p orbitals. Let's look at that carbon atom. How many pi bonds are on that carbon atom? 2, because it has 2 unhybridized p orbitals. Okay, let's actually answer the question now. What's the hybridization of this carbon? sp again, because 2 electron domains, 2 atomic orbitals, 2 hybrids out. Okay, next carbon. sp3, sp3, sp, sp. That's it. All right, so that's A. Okay. How many unhybridized p orbitals are required to make this molecule? Unhybridized p orbitals. There's a couple ways we can do this. We could go through each carbon one by one. Remember when I asked you, this carbon has how many unhybridized p orbitals on it? 2, because one of the p orbitals is involved in hybridization. The other 2 are untouched. How many unhybridized p orbitals are on this carbon? 2, so that makes 4. What about this carbon? 0. What about this carbon? 0. What about this carbon? 2 more, so now we have 6, and then this one, 2, so that's 8. So 8 unhybridized p orbitals are required. But let's do it another way. Let's do it another way. How many pi interactions are on this molecule? 4 pi interactions. For each pi interaction, how many unhybridized p orbitals do we need? 2. So 4 times 2 equals 8. 8 p orbitals are needed. So 2 ways to get the exact same thing. Which way do you like better? The second way? The second way. But it's the same thing. It's the same thing. Yes. Does this molecule exhibit resonance? No. No, there's no way to move around the electrons. There's no way to delocalize them. Those pi bonds are locked into place. There's nowhere else you can put them. Okay. Okay, what's next? Okay, well, we'll just finish these ones. We're going to do this one first. Okay. All right. Okay, 45. According to MO theory, the combination of 2 py orbitals oriented perpendicular to the internuclear axis of O2 will produce which molecular orbital or orbitals? Yeah. So we have oxygen bonding with oxygen. So where are the p orbitals? Are they oriented this way? Okay, that's not straight. This way? Or are they oriented that way? A or B? A, yes. So we have 2 of the same orientation there. That's perpendicular to the internuclear axis. So when I bring these 2 together, what kind of interaction is this? Pi, right. So can we eliminate a lot of these? What are we focusing on? 4 and 5. Those are our pi interactions. We know that because of the 2 degenerate levels, that there's one perpendicular axis this way, but then there's another this way. All right. So it's 4 or 5. Do we know which one it is? Do we know which one it is? No, we don't, because it just says 2 orbitals. We don't know if it's in phase or out of phase. So it's actually going to be both 4 and 5. That we have a pi interaction and a pi star. Let me explain it another way. So remember, the number of atomic orbitals you put in is the number of hybrid orbitals you get out. That's like a rule with linear combinations. So the number of atomic orbitals, wave functions you put in is the number of molecular orbitals you get out. So these are 2 atomic orbitals that we're combining. So how many molecular orbitals do we get out? 2. One of them is going to be bonding in phase. One of them is going to be antibonding out of phase. And so that's why the answer is 4 and 5, because 2 orbitals, 2 wave functions go in, 2 molecular wave functions come out. Yeah, that's linear combination. All right, what was the other number we wanted to do? 25. Y'all skip around. Oh, come on. Oh, good. I already gave the equation. Okay, perfect. Okay, I already gave the equation. Great. All right, this is the hardest question from chapter 4, solution chemistry. Here we're mixing 2 substances, 2 aqueous solutions. You know, we make some type of precipitate. What's the concentration of chloride remaining? So I already gave you the balanced chemical formula, but you could also get it yourself. It takes a little bit of time, but you can get it yourself. You swap ion partners, you predict what your product is, what the solid is, and you balance it. So that's what this is. So this question requires a BCA table. I suggest on the exam, just like I said for midterm 2, unless you can knock this out of the park in a minute, just skip it and come back to it at the end. All right, just guess. All right, so, and we even try to give you easy numbers here, because when you use a BCA table, we're given molarities, but we can't put molarity into this BCA table. What's the unit have to be? Moles. So we need to convert moles of our reactants so we can put into this table. We can figure out what the limiting reactant is. So how many moles, given this information, how many moles of silver nitrate are present? 1 mole. 1 liter times 1 molarity is 1 mole. What about barium chloride? 1 mole. Awesome. Because 1 liter, 1 molarity. Again, we try to use easy numbers. What about the products here? How much silver chloride do I have? 0. Barium nitrate? 0. Okay, great. So remember in chapter 3 how we did limiting reactants? I said, you know, calculate it twice, figure out which one produces the least amount. That's your limiting reactant. But just look at these numbers and think, okay, which one's going to run out first? Which one? Silver or barium? Silver, because you're using it twice as fast. You start with the same amount of both. So silver is going to be limiting. So if silver is limiting, we're going to use it all up, right? We're going to consume it all if it's limiting. So what number goes in the change line there for silver? 1? -1. -1. We consume 1 mole. We consume, now, remember, the change line is always, everything in the change line is dictated by stoichiometry. If I consume 1 mole of silver nitrate, how much barium chloride do I also consume? Half a mole. And it's consuming, so it's minus. If I consume a whole mole of silver nitrate, how much silver chloride do I get? +1. How much barium nitrate do I get? Half. Then you just add everything up. So after this reaction is done, I have half a mole of barium chloride aqueous present in my solution, in my beaker. Like if I, could see atom molecules and stuff, and I looked in here, I would have half a mole of barium chloride. I would have 1 mole of silver chloride solid, and I would have half a mole of barium nitrate aqueous. The states are important here. So let's answer this first question. How many grams of silver chloride are produced? How do I get that? It's just 1 mole. So whatever this is in grams, that's how much you make, right? So the BCA table tells us how much we make. So just convert 1 mole of silver chloride to grams. There's your answer there. But now the harder part is what's the concentration of chloride remaining after the reaction is complete. So concentration of chloride is equal to moles of, so someone said moles over liter, great, I love it, but let's be specific. It's moles of Cl minus over liters. So we need to figure out how many moles of chloride are in solution. So let's look through everything. There's no silver nitrate. Does barium chloride contribute chloride ions? Yes, it does. So we're going to focus on that. So if we have half a mole of barium chloride, how many moles of chloride are there? 1, yes, 1, because there's 2 chlorides per every barium chloride. All right, okay, equals 1 mole of chloride. Let's be complete. What about silver chloride? Does this contribute chloride ions into solution? No, why? But there's chlorine there, there's a chlorine. It's a solid. So if it's a solid, is it floating around in solution? No, it's at the bottom of the beaker. It's not in solution. So we don't count that. And then barium nitrate doesn't have any chloride, so we can ignore that. All right, so then the answer is 1 mole divided by the total volume. So it's over 2, so it's a half. Cool. What if I asked, what is the concentration of barium after the reaction's complete? What is it? It's the same thing. You look at where are all my sources of aqueous barium. Here, there's half a mole there, no barium there, another half there. So 1 mole of barium divided by 2, another half mole. So in that case for barium, there's 2 sources of barium, 2 sources, and they're both aqueous. Okay. 10 minutes. 10 minutes. 28, so I can scroll less. All right. 28, which in the activity series, which metal can be used to remove aluminum ions from solution? So remember the activity series. What's the rule for the activity series? A redox reaction will happen when the metal is, yes, above the thing. Yeah. When the metal solid is above the what? The cation, yes. So our cation here is aluminum 3+. So we need to look at the activity series and find the substance that's above aluminum 3+. So, okay, where is it? I don't know. So you look at the thing, all right, you locate where aluminum is. It's right here. All right, so we can pick any one of these solid metals above it. We cannot put the cation above it. We cannot put the cation above it. It has to be the metal. All right. All right. So I guess the answer is none of them. I think it's none of them. Yeah. Okay. Yeah. So a really good question, I think. Here, let me just screenshot this real quick. Okay. Okay. Real quick here. Okay. All right. I have a mixture of iron 2+ and or no. Okay. I have iron and copper, and I want to separate them. How can I separate them? Yes, you can. Yes, a redox reaction. Very good. But what substance do I want to put in there to make a redox reaction happen so I can separate iron and copper solid? What do we want to put it at? There's a lot of things that we can use. Okay, so let's highlight this. So iron is right here. Copper is right there. So remember the rule for redox reactions. A redox reaction will happen when the metal is above the cation. So if I put silver, if I added silver plus into this mixture, will silver plus react with copper? Solid? Yes, it will, because the metal is above the cation. Will silver plus react with iron? Yes. So if both of them react, we get iron 2 plus and copper 2 plus. Now they're in the solution. Does that help me at all in separating them? No, I had 2 solids. Now they're both dissolved. That doesn't actually help me at all. Okay, so I actually don't want to pick silver. I don't want to pick silver. Adding silver plus to both of these will turn both of these solids into their ions. That's not helpful to me. Okay, what if I added zinc 2 plus? Will that react with iron? No. Will it react with copper? No. So why would I add that? It's like adding water. It does nothing. Okay, so what should I add? Anything in the middle. Yes. So let's say I add HCl. What's going to happen? Is HCl going to react with copper? No. Is it going to react with iron? Yes. So you're going to make iron 2 plus aqueous. It's going to be swimming around in solution. But what's stuck at the bottom of your beaker? Copper solid. So you can just skim it off. Okay, skim off all the iron 2 plus into a separate beaker, reduce it with something else, and there, now it's separated. Right? So using the activity series, you can say, okay, let's pick something that's reactive with this, but not that. And you can separate stuff. Just like solubility. Okay. Yeah. You got to speak up. All right, so for 46, yeah, if you're leaving, that's fine. Just be quiet and be respectful to your classmates who still want to learn. Thank you. Okay, all right, or stay, whatever. Okay. All right, yeah, 46. According to MO theory, which will produce a shorter bond when electron is removed. All right, so this all has to do with bond order. As bond order increases, strength increases, but length decreases. Yes, there's a lot of different ways we use to calculate bond order, but specifically for MO theory, we use number of electrons in bonding minus anti-bonding over 2 gives us our bond order. So if we remove an electron, that's what we're doing. We're removing an electron. We can either remove an electron from a bonding orbital, or we can remove an electron from an anti-bonding orbital. So let's just think about this conceptually. If we remove an electron from a bonding orbital, how does the bond order change? It gets weaker. Yes, bond order goes down. So what happens to the length? It increases. Yes, length increases because we weaken the bond. Bond order goes down. But what if we take an electron away and it happens to be from an anti-bonding orbital? Bond order actually goes up. Yes, so then the bond gets stronger and it gets shorter. So here's a way you can kind of speed up the process. If we look at the things here, all right, these diagrams. Oh, I got a screenshot on that, sucks. All right, so we're using these diagrams as long as we think, okay, are we adding removing an electron from a bonding orbital or an anti-bonding orbital? We don't actually have to calculate bond order. We can just conceptually think, okay, does the bond order increase to get our length to decrease? So let's look at F2. So what I want to do is draw the actual MO diagram first. So for F2, we want to add 14 electrons total because there's two fluorines, each fluorine has 7 valence electrons, so that's 14 electrons each. So when we remove an electron from this molecule, which one are we taking from? Which electron are we taking? The top one, yes. What kind of orbital MO is that? Anti-bonding, specifically it's pi star. So do we strengthen or weaken the bond? Strengthen, bond order goes up, length goes down. So what are we looking for? Shorter bond, yeah, so F2 is an answer. All right, next is N2. So N2, can we use the same graph diagram? No, we got to use this one. So nitrogen, 10 valence total because there's 2 nitrogens. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Remove an electron. Where are you removing it from? Bonding. So you weaken the bond. So you lengthen the bond. You can calculate bond order too, right? If you calculate it, you see neutral, the bond order of nitrogen is 3. But if you remove an electron, the bond order is 2.5. But you can just use, you know, concepts here too. So no, nitrogen gets longer. Okay, C2, there's 8 valence electrons. So I think we just need to remove those. So we remove electrons from what kind of bond? Orbital bonding. So it gets weaker, longer. So that one's not right. Okay, but what about O2? So oxygen has 12 valence electrons, something like that. So we remove an electron from what orbital? Anti-bonding. So we actually strengthen the bond. Bond order goes up. It goes from 2 to 2.5 if you actually calculate it. Strengthen the bond, we shorten the bond. So there we go, those 2. There we go. And so same thing, we could ask this question. If you make an anion, add an electron, same idea, add an electron, think, are you adding it to a bonding orbital to make it stronger or an anti to make it weaker? Okay. Good luck, guys.
I hate to ask you this.
Oh. Yeah, what's up?
I'm just gonna ask. I remember